Now remember that we have another element which is decoding function, and the decoding function is again a function which actually takes the embedding and simply predicts the similarity metric. Here we are defining decoding function as a softmax function where numerator provides us the e raised to inner product of two nodes u and v for which we are actually creating a node divided by summation over all e raised to all the inner product of all the nodes in a v. And this particular quantity is nothing but the probability of v in a neighborhood of u. Here t denotes with the length t equal to 2, 3, 4 depending on this one. And this is again is the same. What we are interested in general is learning this ZU such that using the data we have such that probability of NRU or in general all the V can be predicted. Okay, this should be V belongs to NRU. As I told you, PT U given V is the probability of visiting V on a random walk of length T starting from U. We are going to minimize the loss for the learning the embedding. Now here, I keep showing you the same loss function because every time I am changing the loss function to get to the what we have started with. So remember that earlier I have PT V given ZU in the previous slide, summation over them. Now I am changing same bit by substituting because we are interested in predicting this probability. To predict this probability, I showed you that I can use decoder which is fdex ZU ZV which can be constructed using in this manner. And what I am interested in again learning ZU ZV for all the pair of data I have, training set data I have in a random walk for each node. And hence this will become again the probability of U and V co-occurring on a random walk. So here we look at it, we have moved from solving the problem of U given V or finding out the probability of happening a random walk or given U what is the probability of V being in the neighborhood to our standard problem of encoder decoder where if you look at it, it will be this will be nothing but f of A and C and this is a similar structures which we have seen in the factorization methods. Hence, we have now actually found out the way of finding out F, I and C by minimizing the embedding such that the probability U and V of co-occurring on the random walks can be used as a similarity metric. Now, there are certain catch in it. One of the major catch in here is we have to sum over all the nodes to actually find out the loss function, and it's computationally expensive of order number of nodes. So if number of nodes are in a million, billion, you have to do very large, expensive computation. However, to avoid those kind of computations, people have come up with a strategy. There are two ways people solve, the researchers solve random walk embedding problem. One is a deep walk solution, another one is node to vec solution. In deep walk solution, we will use hierarchical softmax as our tool for reducing the computational complexity. In a node to vec solution, they use noise contrastive approaches for solving the same problem. In this particular course, we will concentrate only on deep walk solutions. However, we will also teach you how to implement node to vec solutions, which are a little bit different from each other in certain aspect of how we actually generate the walks. And you can find details of node to vec in this particular publication. So let's look at deep walk solution. What is the hierarchical softmax? As we discussed, computation of denominator here is expensive. When n is very high, means number of nodes are very high. So what we are going to do is we are going to construct a binary tree where each leaf in the tree represent a node in the original graph G. Okay. And then what we are trying to do is we are trying to predict the probability of probability P of node V given the embedding ZU for each V in the neighborhood of U. But to perform this task, which we are actually interested in maximizing the probability in general. So here what will happen is that instead of looking at all the nodes, we are going to look at certain specific paths in the binary tree to predict this one and maximize this probability and maximizing this probability. So what will happen when we will have a binary tree? So we will have a path to the node V as a sequence of node, where first one is the root node, which is B0, and then there will be intermediate nodes, and there is a final node which is going to be V. I'll come to this ln n in some time. So this is a final node, which is actually the node for which we want to find out the probability given our embedding. Now, if we look at our original problem, then we can actually, under certain assumption of independence, we can again put it as a conditional probability, where I am conditioning each probability of going from ZU to certain node in the binary tree, which is BG, and my total probability of V given ZU is becoming the probability over a specific path from root node to V and their products. And here the n ln n basically tells you how many nodes for which are there between roots and the node V. So let's look at more detail, and also remember that when we have this probability, we can actually model this probability as a binary classification with ZU as an input. Because we do not know which specific path to follow, we can actually use binary classifier to see whether we have to go to particular visit particular node or not. So we constructed a tree for a graph with the nodes 8 here, where root node is B0, there are a set of intermediate node, and each of this leaf node is node of my original graph G. Now, what I am interested in is, let's take a simple example. I am interested in finding out the probability of node U4 being in a neighbor of node U1, and I want to learn this embedding, given embedding based on that. So, I am interested in finding out probability of U4 given Z U1. So, now I have to find out this sequence. So, if you look at it, I have a B0. If you look at the path, B0 to B1, B1 to B4, and B4 to U4. So, I have a B0, B1, B4 and U4 as my specific path from B0 to U4. And now, the question we are going to ask is, how can I actually compute the probability of U4 given Z U1, which I have already shown you can be given as product of probability of visiting different nodes given a ZU1. Okay, so I have to find the probability of these two. So, if you look at it, it is a B1 given ZU1 into B4 given ZU1 into BU4 ZU1. Now, the question is how to find these probabilities. So, what we are going to do is, we are going to use certain interesting structure of binary trees. So, in a binary tree, either I can go left or right. So, if I know the left probability, 1 minus left going to be probability of right or vice versa. So, here the probability of taking a left path given embedding ZU is equal to 1 minus probability of right path given ZU. Okay. And this probability can be calculated using training samples. Now, how we can do that? So, what we are going to do is, we will start at B0. Of course, the path has to start with B0 as a starting point, and we will try to compute the probability of going left given B0 and ZU1, and probability of going to right given B0 and ZU1. And this can be modeled as a sigmoid function f of inner product of between ZB0T and ZU1. If I do that way, I can also get right probability, because 1 minus left given B0 ZU1 equal to sigmoid minus ZB0 transpose ZU1. So, this is interesting property of the system, and here ZB0 transpose is an embedding of internal nodes, which we are going to learn from the training samples simultaneously. So, if with this particular probabilities, what we can do is, we can predict what is the probability of B1 given B0 ZU1, which is equal, which if you look at our graph, this is the path we have to follow. So, we have to find out the probability of B1 given ZU1, probability of B4 get Z1U1, and probability of ZU4 given ZU1. Okay, so I am trying to find out those probabilities here, which is going towards left, probability which we know from here. Similarly, if B4 is in right side, so we have to predict the probability of this one, ZU1, and similarly of Z4 given again right for U4. Hence, we can actually calculate this probability from the data and using the sigmoid and some embedding function for ZB0. So here we have probabilities. Now the interesting fact here, if you see that while visiting on the binary tree, I have not visited all the nodes. I have only visited ln nodes. So if you look at, we have a 8 and ln of 8 will be around approximately 2.6 or 7. It's a 6. Then this will become only visiting 2 internal nodes. So we have not visited all the N8 nodes. It is just ln nodes. So it reduces the computational cost while we ensure that we have found a probability of U4 being in neighbor given U1. What we are interested in, maximizing probability of co-occurrence of U1 and U4. Hence, we can actually add this one and try to maximize to such that maximize this probability and learn the embedding. Here I have talked about only one node in the neighborhood. If there are more than one set of nodes are there in the window, we have to maximize probability of co-occurrence of U1 with all those probability together. Now, one more question someone can have is how to construct the binary trees. In many applications, you can actually construct binary trees in a systematic manner. For example, I have given you one of the biological example here, where tree constructed based on the relationship between nodes using some kind of biological significance. So here we have actually used enzymes to actually construct the binary tree, where the 0 denotes the particular in general enzymes, 1 denotes hydrolysis as enzymes, 2 as a transferase as enzymes, methyl transferase and transcatolase are 2 kind of transferase enzyme kind, and based on that each of these particular proteins have been, I would say, distinguished in a binary trees, and we have constructed binary tree in this manner. Let me summarize what we have studied today. Node embeddings is all about learning a latent representations of encoders such that similarity matrix, it can be deterministic similarity matrix like adjacency matrix or some higher order matrices, or it can be stochastic matrices like probability of co-occurrence between 2 nodes in a neighborhoods, such that we preserve the graph and embedding domain. Such this matrices has to be preserved in both graph and embedding domains. So if we want to learn latent embedding in this particular manner, we have studied 2 kinds of approaches. One is factorization based approaches or methods, where we have studied how we can factorize a matrix, similarity matrix, to learn the embedding. And another one which we have learned is random walk based methods, where we have looked at only deep walks and used hierarchical softmax approach to find out the embedding, stochastic embedding, you can say that. In general, random walk based approaches are more efficient in terms of computation, because as we discussed, it will take a less amount of computation. For a large systems, we do not have very efficient singular value decomposition kind of algorithm sometimes, so we prefer to use random walk based approaches. Now many times there is a question which method to choose for the embedding, because we have several methods. Now that question is difficult to answer often. There is a nice study by Goel and Ferreira which compared some of these embedding methods. We can look at it, but based on experiences of many researchers, when it comes to choice of embedding approach, it depends on the application of interest. What we have to look at is the similarity metric which we have used to define the co-occurrence of two nodes. We have to choose method which actually deals with the similarity matrix for which our application of interest has the same kind of similarity matrix to be optimized. Okay, so if there is an application where the adjacency matrix itself is a good similarity matrix, then we should go for the graph factorization method, or we do not have any idea about it, if the probability of occurring two nodes together is good similarity matrix for the particular application of interest, then we should go for the similarity matrix. Here I am summarizing all the methods which we have studied or we have mentioned in this particular lecture. The first one we have looked at was the graph factorization. Then we have looked at the graph wrap. We looked at the hope. We also looked at the Laplacian eigenmaps, and we saw that the decoder types are a bit different from one factorization method to another factorization method, and also the similarity matrix, and somewhere also loss function is little bit different from one to another one. Here again we can see in a deep fork and the node to vec, the decoder has the same kind of structure, which is the softmax probability of co-occurrence is done for the decoder. The only difference with the similarity measures which are used here, and one we use unbiased random walk, another one we do the biased random walks, strategy of random walks, and try to see the loss functions is remaining the same. Here it is f of DEC which has to be taken care of. And these are some of the references where some of these methods have been discussed.